Thank you. How's the audio? Are we good? Sweet. Okay, this is achieving functional programming in Java. This is something that I spend a whole lot of time thinking about how to do. If this talk was called like achieving FP in like Haskell, it would be like one slide that just said like write Haskell, and the rest would just be like a crossword puzzle or something. But in Java, this actually requires like quite a bit of thought and effort to get this right. And there's a bunch of reasons for that. Before I get started, I should do this whole sort of reminder that you can rate this session with the GOTO Chicago app, I guess. And then you can also submit questions to that, but I would actually like it if you have questions to just sort of raise your hand and interrupt me, because some of this stuff is sort of like, there's sort of this like natural matriculation from like simpler concepts to more complicated concepts, and so rather than just like sacrifice understanding something early on and then like forfeit the rest of the talk, just like interrupt me and we'll talk about it right then. Or if you don't feel comfortable, we'll get to it at the end. So I guess first a little bit about me. I am a software developer at an algorithmic trading firm called DRW. They're headquartered here in Chicago. They're actually not too far away from here. And I spend most of my time at the company working with the trading infrastructure teams. So for just a very brief amount of background on that, you could think of the company of DRW as like I like to use the analogy of it's almost kind of like a startup incubator for trading desks. So we may spin up new trading strategies pretty regularly, and you can imagine that it becomes pretty quickly cost prohibitively expensive to assume that you have to re-engineer everything that you might need to run a profitable, like successful trade from scratch every time you try a new strategy. And so there's some common software that you end up needing basically regardless of what you're doing. Involves tracking P&L and doing sort of, obviating things that make it easy to reconcile at the end of the day. There's compliance problems and all sorts of stuff. And so the TI teams, trading infrastructure teams, spend a lot of time writing this software that is basically the entire firm is their customer. And so reliability is absolutely paramount for as a requirement of the software that they deliver. Unlike a product company where you might have, deadlines because you're trying to pitch an investor on a feature that better exists next week. We are more under the gun to make sure that things actually just work. They're reliable. If things go down, it could be extremely expensive for us. And I'm also the maintainer of Lambda, which is the open source library released under the MIT license that I'm going to be talking to you about mostly today, which is basically what we use at DRW to facilitate FP in Java. And so just a very brief background on the developers. We actually probably have some of them in here. They're polyglot devs. We maintain applications in Ruby, C#, Clojure, and Java. There may actually be some more floating around out there. Those are just the server-side languages too. We have full front-end stacks as well. And by about right now, I think there's approximately 30 or so applications that are built on top of Lambda. And when I say built on top of Lambda, I always make the joke that if for whatever reason, or the SEC or the CFTC has a big problem with something that we've written, I'm going down because com.jnape is in absolutely any stack trace that might get thrown. So I'm going to jail or something. Okay, so I have to confess that I actually knew I was going to do this talk about a month and a half ago, and I put a bunch of slides together, and I felt really, really good about them. I felt like there was this obvious inductive step from early concepts to later concepts, and it seemed very clear and coherent to me. And I presented it at a user group in Milwaukee, and I had about an hour, 5 hour, 10 minutes to present, and I got through about 40% of the slides. So I basically trashed all of those and said, forget it, I'm just going to cover some basic stuff here, and then if we have time at the end, just crack open IntelliJ and just play around and maybe answer some questions or show you guys kind of the ergonomics of how this actually works in practice. But to get there, let's talk about some guiding principles that we tend to follow on the teams that use Lambda to program effectively. So the first is that constraints should be precisely stated via types. We actually think a lot about this. This is something that's become sort of second nature, but we think about, we have sort of propositions, logical propositions can be represented by by like axiomatic set theory, which can be represented by like Bertrand Russell's type theory. Like these things are equivalent. I can start with any one of them and I can recover the other two. And so when we want to talk about like what is the logical proposition that we want to be able to satisfy it, like in type check, we want to think about like what type precisely specifies the constraints of my system. So like we're not going to use a list if this thing could at most have 2 elements and at least have like no elements. We'd probably create like a custom data structure for that. Or if we have like 1 of 2 values, we're not going to represent that as like 2 possibly missing values. Like we wouldn't say like here's 2 slots and like both of them are like maybes, because that would model like only half of the correct representations. There would be 2 like totally impossible representations that we would have to handle in order to satisfy the type checkers. That would just not, that wouldn't work. The second one seems like a tautology, or like seems like self-evident, but it's remarkably like hard to find, evidence of this in like the JDK. Generic operations should have generic interfaces. We get a lot of reuse from being able to model things as like functors and applicatives, and we get a ton of stuff for free. That's like correct by construction because we have these general interfaces that we can adhere to. We don't have to re-implement like HMap every single time we think about like mapping something. Lazy eval is a useful default. I am not going to preach to you that lazy eval is like strictly better than strict evaluation, but certainly it's a useful default that we have gotten a lot of use out of. Partial operations should be encoded as total operations. So what do we mean by partial operations? You can think of when you're like type checking in Java, what the type checker is doing when it's trying to unify your expression to determine if like the right-hand side like can like satisfy to the left-hand side. There's all of the like instance inhabitants of that type that it's looking for, but it's also looking for what we would call bottom. So it would say if this program diverges, if it throws an exception, or if you return null. Null is universally polymorphic, so like there's no way to type check in Java currently that like something isn't null. You just have to like check at runtime. Or you could have like a while true loop, like you could have like non-termination. Any of those are examples of diverging, of basically like the type on the left-hand side, like the type checker kind of saying like sure, like it'll work, but then when you run it, something goes wrong. So what we would tend to do is we would try to encode those partial operations, things that could throw, those are the most common occurrences. We would try to encode them as total operations and say, instead of throwing, we'll return either a special value or we'll put it inside a data structure that actually is like coherent with exceptions and doesn't pop the stack and like blow your application up. And then the last thing is that pure and impure operations should be separate. They should be separate both in how you can type check them, they should be separate in how you design your applications, and we should be able to think separately about them. We can refactor one of those with like a ton of confidence, and the other one, like, did it like fire missiles or like format my hard drive, or I don't know. I want to be very careful about the separation there. So let's sort of step through these systematically and take a look at like what I mean by each one of these things with examples. So constraints should be precisely stated data types. Here's maybe a good starting example. Let's say that we have some method in the ether that's like exists and it takes a string and returns a Boolean. But in actuality, like string is a pretty poor type for most representations. Like almost, is this like call me maybe, like the lyrics to it, or is this, the like bytes of some movie somewhere? Is this a gigabyte? Like you don't know very much about a string. And if this is a UUID, use a UUID. Similarly, I talked about this a little bit earlier. If we want to split a float into like its integral and its fractional parts, a list is like has no opinion about how many elements it has. It could be empty. It could have 100 million things in it. That's not a terribly good use of that. We would use a lambda type for this. We would use a tuple 2, and we would say what you get back is definitely like 2 integers, no more, no less, and there's no way for you to not get integers back from this. And here's something that might seem contrived, but I used to run into this thing all the time. I'm actually being a little bit more like forgiving with my interfaces than what I would usually run into. Usually what I'd run into is list of object, but I chose like the minimally contravariant type to string and integer, like the nearest ancestor is actually serializable. So let's say that we have a list of some items that could be strings or could be integers. And really those are the only things that it could be. Those are the only things that we want it to be able to be. But the reality is that in Java, really your only option by default is to choose the nearest ancestor, or like the furthest ancestor if you just want to say object, and then cast, right? Do like instance of checks and cast down and deal with the things, you know, in isolation. And so let's say we want some integer value, and if it's a string, we're going to call length on it, and if it's an integer, we'll just like take it as it is. The type checker is going to, you know, sort of warn us here that value won't be. Can you guys see the cursor up here? No, you can't. Okay. So that value won't be initialized without that else. So like if we're going to use the value later, we need to guarantee that we wouldn't have gotten to that point by then. So we need this else clause. And really, this is this is pretty crappy. Like this sort of sucks. Your interface is like far too permissive for what you actually want to support. And it actually gets even worse than this. If at some point in your application where you actually pass this list of things to process, if you have a requirement that says like, hey, we now want to support like doubles or floats or booleans, the type checker is not going to tell you that you missed a spot. You're going to have to wait until it just blows up. Hopefully you've got tests around this, but like these types of methods, when they intermix, they can become like combinatorially complex like very, very quickly. So what we would do using Lambda is we would actually represent this list like our very first, our first decision would probably be to represent this list as a coproduct. And a coproduct 2 is a type-safe way of basically saying like, I don't have both of these things, but I have one of these things. And it gives you like exhaustivity matching where it exposes like a single interface that basically says like, I have either a string or an integer. So if you want some type R, and you give me a way to go from a string to R, and you give me a way to go from integer to R, I can promise you can get an R back. Like I don't know which one I have, but I know you're going to get this R back. I know this is going to work. And so the nice thing about this is if we decided later that this actually wasn't just a string or an integer, that now it could be a Boolean, we'd have to promote that coproduct 2 to a coproduct 3. We'd have to specify it at the type level, and we get compile errors. So the type checker would actually tell us that we don't have an exhaustive match anymore on line 3, whatever that would be. And so we'd have to actually fix that. But then once we actually got it compiling, we would have a pretty high level of confidence that we covered all the cases and that our feature's done. This is a sort of interesting phenomena that doesn't really make it into Java very often, but I've seen this happen quite a bit in Ruby. In Clojure, it's pretty prevalent as well. In Go, it's like absolutely ubiquitous. It basically says like, I'm going to try something, and I'm going to give you back like either an exception on the left-hand side or like a success on the right-hand side, but I'm going to represent it as two values. You know, if any of you guys have ever written code in any of those languages, you may say like underscore, comma, OK, or like EX, comma, OK, or something like that. I alluded to this particular issue earlier. Tuples of like maybes or like optional values is like a really poor way to represent that in my opinion, because there are 4 constructions of that type, and 2 of them are absolutely invalid. So like half of the representable things are completely impossible. But like now you have to manage when the type is kind of like lying to you. You have to remember like, oh, we actually don't care if both of these are nothing or if both of them are present, because that shouldn't be possible. So we would just use an either type, which comes from Lambda, to represent that it's one of these 2 things. And either is just like a coproduct 2, but it has implicit success and failure semantics. So it has like functional comprehensions on it that allow you to speak to it in terms of like, this was something that went wrong, and here's how I can recover it to a better option. Or I can say like, or else, or I can say like, forfeit the good, you know, the good thing that I wanted back to the bad thing. I have lots of different ways I can operate on that. So the second thing is that generic operations should have generic interfaces. This is like maybe a cheap shot, but it's so easy that I just can't like not fall for this trap every time. So since Java 8, all 4 of these types got added to the JDK. We got a function type, we have an optional type, a stream type, and a completable feature. Those probably for the most part are pretty self-explanatory. Function is a little bit different than the other 3, but effectively we can talk about all of these things as saying like there's some type that have the potential to offer the thing on the right. Like they have the potential to offer like an integer. And that integer is covariantly positioned. So what that means is that we could provide a function that would take that integer as its origin and could map it out into something else. So if I gave you a function from like integer to float, and you look at a function from string to integer, you should be able to say like, well, I can just compose those naturally and get from string to float. Or I could like update the optional and say like, hey, I don't know if you had a value, but if you did, I want that value turned into a float. And so we've got like 4 different ways of doing that. We've got like function.andThen, which is this totally like unique operation that exists on function. We've got optional.map, We've got stream.map, which starts to like maybe be a little bit encouraging that we have like the same semantics used. And then we got future like .then apply. And even between the two map operations, there's no common interface for any of these things. So pretty much every time you run into this like extremely degenerate case, you have to kind of re-implement it, come up with like another semantic for it potentially. And you get absolutely no way to program generally against this. All right, so anyone who's worked in like Haskell would take a look at this and probably immediately say like, well, that's a functor. And you'd be right. And so in Lambda, we actually have a functor interface that we can model as a first-class concept. And we can also program against it generically. So we could have like a response envelope, for instance, where we parameterize the body. And then we could, we would have to implement what HMap would look like for that response envelope. We don't have any like auto-deriving or anything like that. But we would at least be able to talk about this thing uniformly as like a functor. And we'd be able to write operations that take a functor of some type A and like a morphism from A to B and produce that functor back of some type B. And so we have like functors running all over the place. And if it seems a little bit cheap to go to functor, like functor is honestly not that powerful. Like you can't really do that much with HMap. It's not really that like great of a tool to program generically against. But here's another example. Here's using HMap on those things. There's another example, which is flat map on optional. So optional has a flat map operation, basically says like, if I have this value, I can return a new optional and potentially like crush them down and say like, if I didn't have a value, it remains nothing. If I did have a value and my function returns an empty, then I'm going to remain empty. And if I did have a value and my function returns like a present value, then I'll remain a present value. So it's a way to sort of map into a new instance of the same type and then flatten the layers. Stream has the exact same operation. It's even called flat map. Completable future has the exact same operation, but it's called then compose. This one is really painful to not have a generic representation of because there are lots of like provably correct things that we can do if you satisfy the axioms of flat map. And it's not on function. Function doesn't have any analog to flat map, but it's like very, very easy to implement. If anyone wants to take me to task on that, we can just implement it real quick. If, however, we knew that it was a monad, which would mean it's implicitly also an applicative, then we could do some really, really interesting operations. So here's the flat map on maybe. Maybe is a monad. You'll see that it looks like rather similar to what optional was, just using just and nothing. I tend to, when I have to come up with a name for something, I tend to err on the side of ubiquity. So if something already has a very well-known sort of term that's Googleable, like I want these things to be Googleable. If you have a question about how something works, I don't want you to just have to like troll through Java docs all day. It'd be great if you could just go to Stack Overflow and be like, what's a maybe? But then I can pull some really interesting type level tricks that really don't have anything to do with maybe, that only have to do with the generic operations that maybe promises that it supports. So this is something that in Haskell is like absolutely invaluable. And getting this to work in Java C was a very challenging endeavor, getting this to type check. So none of this is vaporware. You can copy all of this code and paste it in like a main method, and you just need Java 8 or later. And this will all compile and it'll all work. So we can say, hey, if I've got like 3 maybes, really what I do is I want to flip the types. I want to say, forget about me having to check each one in isolation and like fold through this thing manually. Convert it into a single maybe that wraps all the values, assuming all of them are present. And if anything was absent, make the whole thing nothing. And I can get that for free. Just from maybe, sequence is the method that we're calling. It doesn't know anything about maybe. Like there's nowhere in the source code of sequence that has a reference to maybe. It just works on applicative, which means that either, which is also an applicative, works the exact same way, and I get it for free. And we use this operation all over the place. This is extremely helpful. We can see some examples later if anyone wants to see why. Okay? Okay, lazy eval is a useful default. I think it is. We deal with dates quite a bit. So you might imagine that, actually I think we've written a function like basically exactly like this, which is days between using the Java util local date. We'll say we have a start date and we have an end date, and we really just want to like fully populate that. We want a dense representation of all of the dates like through time between those two dates. And so if I was just working against like standard vanilla Java, I would very likely write it like this. I might use a stream. I tend to be very wary of streams. The reason is because they're only iterable once, and they're extremely susceptible to any sort of like warranty voiding. So even if I map a stream, which is a lazy operation, I've effectively like bricked the instance that I mapped. I can no longer interact with that instance without getting an exception. I have to I have to do this sort of like almost linear typing strategy where I always have to retain the latest reference. And if anyone has interacted with that, I better not share it because state has changed. So stream is more like an iterator, and so I tend to like be very wary of streams if I want to generally represent something that's like an algebraic, like linear representation of data. So I'd probably use a list. I probably just like do a while loop, do a bunch of is before checks, add it, and just allocate it on the heap and say I hope you don't give me like 1,000 years between these two things. And of course that's exactly what I'm going to do just to drive the point home. And so list lots of days is now massive, and then it kind of really sucks when later on when it's time to actually read anything from it. It turns out we only needed 10 of them. Now we have like this massive GC that would otherwise have been totally unnecessary. And so the way that we'd probably write that is we'd probably write it like this. We'd probably say, there's some like co-inductive function like iterate that takes a start date and takes a function and will just produce new values till the cows come home, like to positive infinity. And then we're going to constrain that and say just take while that value is less than the end value. And that doesn't run anything until you force it. So until you start yielding values out of it, like nothing happens that that runs in probably like sub 10 milliseconds. That takes no time at all. And so then we do the same exact example, only this time we have an iterable of local dates instead of a list because we actually don't care if it's on heap. And so then we can just say take 10, and we only ever ended up computing 10. And if we really, really want to memoize it for some reason, like let's say this computation is expensive for whatever reason and we only ever want to do it once, we can easily like convert it into a list and then just share the list around if we want to. But like share a list of the dates you actually care about. Well, there's a lot more to say about lazy eval, but in the interest of time, we'll move forward on this. So partial operations should be encoded as total operations. I'm going to move a little bit more quickly because we're about halfway through at this point. So here's another example that I just love to kind of make fun of. Poor JDK guys. Integer parseInt. Like this is obviously a lie, right? This interface is just like a fiction, right? There's no way that I can give you any string and get back an integer from this. There's just no way. Like this is implicitly like this will throw. And in fact, it will throw for like far more values than it won't throw for. And so we could represent it as a maybe and say like, if you gave me, the rain in Spain, I'll give you back nothing. And we do stuff like this all the time. Like it's really useful to be able to parse like unstructured input data that might actually not be valid representations of our domain. And so instead of doing the same sort of integer parseInt trick, in this case, we might actually care, so we deal with fixed messages. If you don't know what fixed messages are, your life is better for it. Effectively, it's just like this like terrible like representation of financial messages that's very painful to parse. We could represent this as an either of like custom errors or failures or a bunch of things that went wrong. And then we wouldn't have to worry about like speculatively being like, well, should I check this input up front? Should I put a try around it? Like when do I need to catch any invocation I'm making in my code base? When should I wrap it in a try? Like how do I know? You have checked exceptions and the type checker can at least force you to deal with it in that way. But checked exceptions kind of aren't a great idea in general anyway, because oftentimes you don't want to impose like what to do. Like the caller just ends up rethrowing in many cases. They actually don't care. And so to allow them to optimistically deal with the result while just being able to focus on what they actually know how to do is much nicer. And that also, I mean, it only works for checked exceptions. Unchecked exceptions can happen anywhere. So there's again, we're trying to get to a point where like compilation actually gives us quite a bit of confidence. And then finally, pure and impure operations should be separate. The IO monad. So here's an example of I don't know, just some stupid, like, I feel like there's an obligatory, anytime somebody's going to talk about functional programming, either you have to do a banking metaphor or like, withdraw funds or something, or you have to do something involving counting lines and like the MapReduce example of, words and lengths. So let's say that we want to, just check every line in some file, split it into words, flatten it all, give me the unique words, and then sort it based on like the longest words. So we want the longest words first, and then just give me the top 10. Like give me the 10 longest words for some path. There's a side effect right in the middle of it, which is files.readAllLines. If I call that with the wrong path, I'll blow up. If I, rm something on my file system, this will blow up. This code is highly, highly, highly susceptible to like state that is externally managed. So I can't really call this with any level of confidence without knowing some other information about, who knows? Like in this case, the file system could be Google's homepage source code. Like who knows? And so what we would tend to do is we would split those two things. We would say actually like the majority of that function is pure, and that makes it very easy to reason about. Our output is directly decidable from our input, super easy to test, really easy to refactor. The types are highly reliable in that case. And then we split out the read lines part. And we say, put that inside of an I/O. And if anyone's interested in more of a deep dive in I/O, I'd be very, very happy to go into that. There are some super cool properties about I/O when you model your application this way. So here we would just say read lines I/O is a functor, in addition to being many other things. And so we could just say read lines, give it the path, and then assuming that everything worked, fmap the function that we actually want to call. And that again, that doesn't run it yet. We have to wait until the end of the world, which is when I/O actually happens, when the thing you're getting paid to do, you actually do. And one of the really nice properties about this, remember the sequence trick earlier, is that we can say, well, what if we had two paths? What if we needed to parse, what is that, I guess, 2 books, A Tale of Two Cities and The Sun Also Rises. And we wanted to figure out the 10 longest words across both of those things. Let's say these are really, really long books. These are slow operations. I can just map them into an iterable of IOs, and then I can do the same type flip and get back a single IO of an iterable of strings. Again, that doesn't run yet. And a really nice property about this is that's implicitly parallelizable. So if you think about what we're doing whenever we're composing, and we're writing arrows from A to B and then from B to C, there's implicit dependency between those two operations, right? I can't call B to C until I've called A to B because I need this as an input to my second function. But what I've just set up here is that these two paths are orthogonal. They're adjacent to each other, like they're neighbors. They don't have any dependency on each other. At some point in the future, I'm going to need the results from both of them, but there's no reason I can't read them in parallel. And so I've composed it that way. I've said, hey, put these like adjacently in some list, and then when I call sequence chooses the least powerful way of composing these things, which gives you maximum flexibility. So it chooses the ability to compose based on the applicative instance rather than the monad instance. So there's no dependency between the two. And by default, this actually will run this on the fork join pool and parallelize those operations. And then when both of them are done, it'll rejoin back and then call flatten on that result and then call 10 longest words on that result. And we could actually give it our own executor if we wanted to. Like if we didn't want to use the fork join pool, which is a good decision to not use that, we could create our own executor and pass it into unsafe perform async IO, and it would parallelize across that executor. Cool. Any questions so far? Or questions people feel like asking, I would say? No? OK. OK, so Lambda offerings. We are about 20 minutes out. OK. Lambda offers a model for functors, applicative functors, monads, and all kinds of other crazy stuff. Common algebraic data types like maybe and either, and plenty of others. Curried functions with specializations like semigroup and monoid, which we're going to take a look at. And what curried functions are for anyone who doesn't know what they are, we'll talk about that. It's, maybe this is a bit, self-gratifying, but I think it's a relatively rich library of functional iteration patterns and open to pull requests if you come up with an interesting one. Type-safe heterogeneous data structures like HList and HMap. When we looked at tuple earlier, tuple is just a specialized HList. Profunctor optics, which is, I would love to talk about those just for like 3 hours. It's very tough to do those justice in any short amount of time, but we'll take a brief look at an example of those. And then the IO monad. There's not really any rhyme or reason for why I chose to like represent each one of these things as bullet points. I just think that those are probably some of the most like essential points. There's more stuff in here too. So we looked at functor. We sort of briefly looked at monad. There's also an applicative. There's a traversable. There's monad. There's contravariant, profunctor. There's a bunch of others. And you don't necessarily need to know what all of these things are. The thing to take away is that when we have generic operations that we can model generically, we get a lot of things for free. And so instead of just reinventing then apply or then compose or whatever, if you can model them in terms of these things, each of these have lots of default methods that you get by providing a like degenerate implementation of one function. So that gives us a lot of reuse. Also, many of these things are like, they behave in a way that's lawful or axiomatic. So we can write property-based tests that like just test the laws. And if the laws pass, like we have high confidence that they won't do anything surprising. Algebraic data types, like maybe in either. We've looked at examples of both of these things. So I can, maybe is lambdas analog to optional. There are reasons that I added maybe instead of just using Java util optional. One of them is so that it can actually be functor and applicative and monad. I've got the expression problem. Otherwise, I can't like elect existing types into those things. Another reason is because optional has some like unsafe operations that I'd rather not offer. And HMap and like map behaves kind of weirdly with optional as well. It's got an either, which doesn't really necessarily have any analog in the JDK. A try type, which is sort of like a try catch finally statement, but as an expression. And composable, so you can compose two try blocks together. You can fmap over the right-hand side. It's actually a bifunctor, so you can map both sides. You have catching semantics on top of try. You have ensuring semantics like finally. You have like a try with resources expression that does the same thing as Java 7's try with resources. It's just basically an expression version of try. Choice 2, which is just like either, but without implicit success and failure semantics. So there's nothing wrong with getting a string back from a choice 2, for instance. There's no function that's like or else. Like, or else what? What's the problem with either of these two things? So choice 2 is what we'd use to just say it's one of these two things, but we don't really have any like affection for one over the other. These, which is kind of an interesting and like uncommon data type, but probably useful anyway, which is just basically saying like I have either a string or an integer, or I have both, but I won't have neither. And unit is probably the last one I'm going to mention here. There's actually a bunch others, but unit is useful because it represents like nothing interesting. It's sort of like, like in Haskell, you'll have like the paren, sort of the unit data type. And it basically says like move along, like there's nothing else to see here. So if I see a function that takes unit and returns an integer, that implicitly tells me this is a supplier, because I can't give it any context that could possibly be used to yield its return value. So curried functions with specializations like semigroup and monoid. Currying is a strategy, very briefly, it's a strategy it comes from the Lambda calculus, and it is a way to represent a function of any arity as a function with a single arity by using scope closure. So if we said we have an fn2, which is sort of like a lambda analog to bifunction of integer, 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 and we're going to say that that's just integer sum, that's actually the same as saying it's a function from integer to a function from integer to integer. That just closes scope over the outer, like the free variable. And so that's actually directly assignable. There's no coercion that's necessary. That's exactly the same thing. Which means that we can, like, partial application as a notion is not really, like, partial application is just application. There's nothing partial about it. It's just application. We could give it both, we could give it as many arguments as we possibly can if we want, but we could also just give it the first thing that it needs and take the result. And then if we wanted to, let's say, like, fix the argument but not actually run it yet, like defer it, then we could, thunk it and then pass that thing around. And now the onus is no longer on them to provide any more information, but we haven't run anything until they force it. And so then we can represent useful encapsulations like semigroup. So a semigroup, very briefly, is a binary associative operation that like can't escape integer. So I couldn't give it like, it basically means, so it's binary, there's two things that it takes, two integers. It should be an associative operation. So however it associates with parens, like f of A, f of BC should be equivalent to f of FABC. Not necessarily commutative. But the thing that's interesting about this is if you represent integer sum as a semigroup, I can give you a fold for free. And then I could graduate that to a monoid. So I could say, hey, if I've got an identity element as well, an element that like f of identity of x is always equal to x, like for summing 0 would be the identity, I can graduate that to a monoid. And then I get the fold that doesn't require the starting accumulator, which I call reduce. And I also get this really, really useful function called fold map. And I can like implement short circuiting with fold map and then reduce and fold all short circuit. If I said like, here's a semigroup over, or here's a monoid over like a list of maybes, then the first nothing I could just like short circuit and not run any others because I know the result's going to be nothing. We do this quite a bit as well. Monoids also compose, semigroups compose, so like going through the effort, which is not terribly much effort once you already have an F and 2, like you've basically got a semigroup, is worth it. Something is not clicking. Okay. Functional iteration patterns like map and filter. We've seen some of these already. It seems my keyboard may have just given out. Sorry, bear with me one second. Well, guess that's the end of the talk. Let's see. Yeah, it's like, I don't know. Does anyone think it's going to work this time? No, probably not.
You're able to read it.
Yeah, all right. Well, okay. So we could say like, hey, let's start with, taking advantage of laziness, let's start with just the representation of all the natural numbers. And yeah, this is pretty contrived, but it at least gives you like a sense of the types of operations you can do. Get the, get the evens out. None of this stuff runs, by the way, until we actually start yielding values. So, like none of this runs anything. Even the map at the end doesn't do anything. But we can say, take the squares and then take the first 100 and then get rid of all the squares that are below 2,500. So start at like 51, I guess. And then group those in groups of 10, and then sum each of those 10s. I don't know. I came up with that like on the fly. I don't know if you'd ever want to do this, but there's a lot of stuff you can do. Oh, it seems to work again. Okay. Let's work. Okay. Type-safe heterogeneous data structures like HList and HMap. Tuples are usually what you're going to want to use for these. Do we have 10 minutes? Is it 10 minutes left? Okay, I'm going to try to blow through these last ones, and then if anyone wants to see anything in editor, we can do it. So, an HList is a heterogeneous list. It's you can think of like normal lists in Java. You'll see like list of string or something. That's a homogeneous list that says that every element is the same type and it's a string. An HList doesn't care about all the elements being the same. It allows you to typify the element type for each slot. So you can say, I have a singleton HList which has one slot, and the value stored in that is a string. And if I cons onto the front of that, then I'll have a different I'll have a different value at the front, but I'll still retain a string in the second slot. And so there's a couple ways for us to construct these. We could start with a nil if we wanted to. There's a static factory method, singleton HList. That's just a convenience. And then if we started with nil and we consed 3 times, right? Remember, this is cons, so it puts it at the front. So say cons 1 makes it a singleton integer, 2 makes it a tuple 2 string integer, 3 makes it a tuple 3 float string integer. And the main reason for the tuples is because it can be a bit laborious at the type level to have to retain this like linearly expanding recursive type signature, which is like hcons of string, comma, hcons of float, comma, and then like just, a one-to-one correspondence from the types to the, to the calls to cons. And also, there's no really easy way, if you just know it's like a singly linked list, to get the third element. You have to traverse it yourself. You have to say like tail, 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 head, or something. Whereas a tuple will give you random access to each one of those elements. So I can call like, on the tuple 4, where I've got a byte short integer long, I can say dot underscore 3 to get the integer out. And then I can also pop the head off of that tuple 4 to get back to a tuple 3. And anyway, it's tuples, like tuples, whatever. Why are tuples not in Java? I don't know. Keyboard. We also have HMaps. HMaps are analogous for maps, what HLists are for lists, perhaps unsurprisingly. The question, though, becomes how do you actually encode the mapping of the value at a key if you want to say that, two keys in the same map, or sorry, like two different keys in the map can point to two different value types. This is no longer map string to integer where every string points to an integer. This key may point to an integer. This key may point to like a list. And I want to know at compile time that I've actually interacted with this thing in a type-safe way. So there's a type-safe key type that is a default key. It's just an interface, so you can create your own type-safe keys if you like, based on labels or whatever you want to do. And then we can, put in HMap, values of the right type. If I was to change that string to an integer by foo key, it would no longer compile. And then I can, do normal map stuff. I can check if, it contains a key or whatever. And then the default interface is get, because how do you know if you actually have set that, key inside the map? But if you're really, really positive, like you're absolutely sure, you're like, I just did it right here, it better be in that map, and call demand, and that'll throw if it doesn't have it. Sorry, I keep having to do this. My keyboard, like, legitimately is somehow not working anymore. So, Profunctor optics like lens and ISO. Let's take a look at a lens, a simple lens that's built in, and then we can look at this more in depth. Or if you, we're running out of time, so if anyone wants to talk about these more, come talk to me after the talk. There's a lens that's element at, just focuses at the first element of a list as a maybe. So if the list is not, if it's empty, then you'll get back nothing. If it's got a null in that slot, you'll also get back nothing. So there's a sort of correspondence between, not being that size or having a null in there. Otherwise, you'll get back the value that it's supposed to be. And this unifies across the list type to the maybe type. So if I try to perturb either of those types, if I changed list on the first line to like string but left the maybe integer, that wouldn't type check anymore. And there's like 3 canonical operations that you tend to be able to do with lenses. In addition to being able to compose them in both directions, you can also say like view the element at it. So just like lift the element out when you focus it. And view is just a function. It's a lambda fn, so it's curried. So I can just pass it the lens and get back a function that will take a list and return a maybe. Or I can pass it everything that it needs all at once. I can say view the first element with an empty list to get back nothing. View the first element with as list 1, 2, 3 to get back just 1. I can also call over to potentially update that value. Again, these are very basic operations that are possible with lenses. And say like, hey, if you had a value, then fmap it, add 1 to it, otherwise don't do anything to it. And then set is just a degenerate version of over that just calls like constantly on the function side. So I can put a value in if I wanted to, right? I can say I have an empty list, set just 1 to the front of it, and now I have a singleton list where 1 is the first element. I didn't talk about ISOs here, but lenses are like a good enough probably example. We can talk about ISOs afterwards if you want. And then the IO monad. So here's a useful example. I already talked about the auto-parallelism capability. Let's say that we had this function threadlog, or this method threadlog rather, that's just going to get the current thread that it's running on inside of an IO, and then it's going to print whatever the message is. If we said, log hello, and then, right, so flat map, remember flat map says I can't run this until I have the previous operation because I might need the previous result to produce the next result. So it sequentializes these things. So hello, and then print world. If I said just unsafe perform IO, that's just going to run it synchronously, and it's going to print hello world to standard out, which is exactly what we told it to do. But I could also choose to say, I'm going to Google like keynote bugs with keyboard after this. So I could also say, hey, unsafe perform async IO to get a completable future back that will be running, right? It'll start running automatically. And even though world won't be printed until hello is printed, they'll probably be printed from different threads. So that is the IO monad. At this point, I was going to do a demo, but I've got 5 minutes, so it's probably best to leave that open for questions. Last slide is, this is Lambda. That's where it is on GitHub. It's released under the MIT license. And there's a Gitter channel too, if that's your thing. I'm in there. There's some other people that are in there that we can answer questions or discuss like new features that should be added or things like that. Remember to rate this session, please. If you rate it terribly, they will never invite people like me back. So like, you know, be honest with your feedback. And that's all I got.